All right, a couple more practice problems for stoichiometry. Just quickly, let's have a review of what we can do. So if I have a balanced, that's not going to work, sorry. If I had a balanced chemical equation, A plus 2B goes to C. Let's do this, plus D. If I knew the moles of A, right, I could figure out the moles of anybody else, right? All right, so what the balanced chemical equation allows me to do is look at the proportion of those guys. So if I knew moles of A, I could solve for moles of B, right? Moles of C and moles of D. If I had 1 mole of A in a reaction, how much B would I need? 2 moles, right? What would happen if I gave you grams of A? Now what you have to do is convert grams of A to moles of A. Then you can use the balanced chemical equation, right? So if you have a stoichiometry problem where you're given moles of something, you don't need to go to grams, right, and then back. You can just plug directly into the balanced chemical equation. So for example, I could take grams of A, figure out the moles of A, figure out the moles of C, and then get the grams of C, all right? What's another way I could give you the moles of A? I could give you the pressure, volume, and temperature of A if it was a gas, and you could then solve for the moles using PV equals nRT, right? N is the moles using the ideal gas law. So that would be another way, right? So you go from pressure, volume, and temperature to moles, balanced chemical equation, to moles, and then if this was a gas, I could also use PV equals nRT to go from there. What determines the limiting reactant and the theoretical yield? And then I suppose the excess reactant, right? So the limiting reactant is the one that we're going to run out of first. And that one, the amount of product that you make from that determines the theoretical yield. I guess also percent yield. So let's say we had a problem and I had to solve what is the percent yield of D? And then I would have to know the actual yield of D. Wow. Yeah, actual yield of D over theoretical yield of D times 100, right? Okay. Then what would I do? If I was given an amount, say 100 grams of A and 50 grams of B, then what I would do is I would take the grams of B, turn it to moles to moles, and solve for how much D I can make. I would take A, I would turn it into moles of A, go from moles to moles, and solve. Right? Whichever one made less would be the limiting reactant. The amount it made would be the theoretical yield, and I can calculate my percent yield if I had an actual yield that they gave me. The excess reagent would be the one that I didn't use up, and I could figure out how much of it was left. No, this is a lot of talking. I'm not sure it helped. Let's do some problems. All right, so here we have hematite is an important ore of iron with excess carbon monoxide, okay, excess carbon monoxide. How much iron can be produced? So it's saying we have 1,000 grams, and sometimes this is a good way to do this. I've got 1,000 grams of F2O3, and I want to know, and I have excess CO, so I don't have to care about it, and it's asking me how much iron can I make? Okay, so here's iron. Right, that's the question. Let's see, we've got grams, pretty straightforward then I think, right? We're just going from grams to moles to grams. So 1,000 grams of Fe2O3 times 1 mole of Fe2O3 weighs, so somebody added this up for you, nice, handy. And then what's the relationship between moles of Fe2O3 and moles of Fe? And it's 1 to 2, all right? And then a mole of Fe weighs 55.85 grams of Fe. And I punch that in. And my claim is, oh no, interesting. I get 6,994 grams of iron. Hopefully you agree. So quick review-y things here. All right, so an important thing, in order to use a balanced chemical equation, I have to be in moles. So that's what I was in. And then where do I get the molar ratio between Fe2O3 and Fe? All right, it's from the balanced chemical equation. There is an invisible 1 here and a 2 here, 1 and 2. Right? Why do we not have to care about carbon monoxide? Because it told me we had more than we needed. We had excess carbon monoxide. All right, well, that was pretty easy. Did we answer the question? We did. All right. Let's see, zinc metal reacts with hydrochloric acid. Balanced chemical equation, it's what, 1 to 2 to 1 to 1, okay. And it tells me I have 0.30 moles of zinc, 0.30 moles of zinc, and 0.52 moles of HCl. How many moles of H2 can we make? Let's see, they didn't give me grams, but wait a minute, I don't need grams, right? Remember, it's grams to moles, then balanced equation. So we're shortcutting the process. We love this. We're starting at moles. Moles of zinc. And then I want the molar ratio now from the balanced chemical equation. Moles of zinc to moles of, what are we solving for? H2. And it is 1 to 1. Let's see, are we done? I could get grams. Do I need to get grams of H2? Nope. Oh, we're done. How about that? It's because if I cancel moles of zinc cancels moles of zinc, I'm in moles of H2, I'm done. Oh, nice. All right. I can do this in my head. I should be like it. Anyway, moles of H2. All right, nice. And then it says we have 0.52 moles HCl. We're already in moles, so I don't need to go from grams. We're here again. I just need to go between moles of HCl and moles of H2. Where do I find that relationship? Right balanced chemical equation, 2 to 1. All right, so mash that in the old calculator, and we get this. All right, I think we answered the question. Did we answer the question? How many moles are produced? So do we produce 0.3 moles of H2, 0.26 moles of H2? Do we produce the sum of the two? Well, that'd be cool. 6 moles of H2? No, that's ridiculous, right? Yeah, well, let's talk about it. So that's like saying if I had 2 cheeses and 1 bologna, right? And there's enough bread as much bread as I needed. How many sandwiches could I make? Well, with 2 cheeses, I can make 2 sandwiches. With 1 bologna, I can make 1 sandwich. So how many sandwiches can I make? 3, right? Ridiculous. So who do we run out of first? Who makes less? H2, we only make 0.26 moles of H2 from the HCl. So that makes this the theoretical yield, right? And this then is the limiting reactant, right? So this guy would be the excess reactant. And what is this then? How would we describe this thing? So it's not real, right? That would be the amount of H2 we could make if we had 0.3 moles of zinc and as much HCl as we needed. All right, nice work by us. One more. All right, acetic acid can be synthesized by reaction of carbon monoxide with methanol in the presence of iridium metal catalyst. Oh, exciting. Okay, so it looks like we need a reaction here. So carbon monoxide plus methanol gives me HC2H3O2. Is that balanced? We have 2 carbons. We have 4 hydrogens. We have 2 O. That's sort of disappointing. It's balanced. Wow. Nice. Anyway, balanced. So it's 1 to 1 to 1. And it says, I have 15 grams. Let me write it here. 15 grams of methanol and 10 grams of carbon monoxide. How much can we make, and what's the percent yield? So 15 grams of methanol. First thing I have to do is go, right, to use the balanced chemical equation, I must be in moles. So I'd have to turn grams of methanol into moles of methanol. Grams methanol. Moles methanol. How do I get this information? Exactly, balanced chemical equation. So we have what? 1C, 4 H's and an O. So that's 4 times 1.008. That's 12.01 from the periodic table, right? Give me what? Let's see. 4 times 1.008 plus 12.01 plus 16 equals 32.04. Let's see, 32.04 grams of methanol gives me methanol, and then I need to get here, so now I can go from moles of methanol to moles of, HC2H3O2. And what's the molar ratio? Exactly 1 to 1. I could stop here if I wanted to, but I need to know how much we make anyway, so I'm going to convert this to grams. All right. Looks like it's 60.05 grams, right? So just add it up from the periodic table like we just did right here, but for acetic acid, it's that. I guess I'm going to mash this in. 15 grams divided by 32.04 times 60.05 is 28.1 grams HC2H3O2. All right, so if we had 15 grams of methanol, that's how much acetic acid we could make. But we also have 10 grams of carbon monoxide. So 1 mole of carbon monoxide is how many grams? 12.01 plus 16, that was easy, 28.01 grams, right, from the periodic table. And what's the molar ratio now from the balanced chemical equation of CO to acetic acid? It is also, oops, I did that backwards, and fortunately they're all 1 to 1. Trouble. And then 1 mole HC2H3O2 equals still 60.05 grams HC2H3O2. You see I'm writing everything. If you have the time, you should do this because it's harder to make a mistake when you do this. Right. Getting 21.4 grams HC2H3O2. All right, so then how much can we make? How much acetic acid can we make? Is it 28 grams or 24 grams? 21 grams, sorry. It is this one, right? This is the theoretical yield. This is, we don't know what to call that guy. That'd be the amount you could make if you could make it. That makes carbon monoxide the limiting reactant. Methanol is the excess reactant, right? We'll have some of him left over afterwards. Let's see, how are we doing here? Let's read the question again. If 15 grams of methanol, 10 grams of carbon monoxide reacted, 19.1 grams of acetic acid, what's the percent yield? All right, percent yield, right, before E equals actual over theoretical times 100. And the actual amount of acetic acid we made was 19.1 grams, and the theoretical yield we just said was 21.4 grams times 100 equals 19.1 divided by 21.4. I get 89.3%. All right. Well, that's it. Those are some more examples. We'll work on some more in class, but that is it. Nice work by, what are we doing here? Titration is also a thing. I'm not sure why that's here, though. Yeah, we don't want to talk about that right now. That's ridiculous. All right, that is actually everything we need to talk about in part 4. It's over, right? It basically boils down to a couple different kinds of reactions, redox reactions, acid-base precipitation reactions, calculating oxidation number, and then finally, bologna sandwiches.